variables mean something else.
If you get used to it, it's very powerful.
Yes.
Okay, good morning. Let's start on last lecture from the series, and I think the most fun. I'm going to show you how to use algebraic operations and handlers to do something weird in a proof checker. I'm not suggesting you should rewrite lambda pi this way, but I think it's an interesting technique, and maybe somebody can use these ideas to do something fun with them. Before we dive into implementation, I think I should review algebraic operations and handlers. So with a quick show of hands, just to know, how many of you are familiar with the theory of algebraic effects and handlers? Okay, so we're going to go a little more slowly. It's actually going to fit nicely with Andrej's lectures. And then we're going to, so first I will review these things and introduce the concepts. And then we're going to see how we can use them to implement variables and meta variables as well in our little type checker. So it's more of a proof of concept to give you an idea of what the possibilities are for algebraic effects and handlers. Also, I should warn you that if you are a true Haskell programmer, you will probably feel a bit dizzy by the end of the lecture. Okay, so, oh yes, before I forget, this is a very good slide title. If you are interested in, or you know somebody who might be interested in a postdoc in Ljubljana, please talk to me. We have a small, vibrant group that is not so small anymore, and we do the kinds of things that are listed there. So I don't know if you know this, but Ljubljana is also a Bauer Center for AI, like on a planetary scale. I think Slovenes have, this was published in Forbes magazine, Slovenes have the highest density of AI researchers per capita. But also yesterday, there was a map on Reddit that shows that we have the highest density of suicide in Europe. So I okay, so talk to me if you're interested, or if you know somebody who's interested, please send them in my direction. Let's go on with algebraic effects and handlers, and tie in with the themes from Andrej's lectures. I'm going to try to draw this line from theory to practice by starting with something very traditional in universal algebra, and we'll just sort of change the types until we get to the programming concepts. So recall that an algebraic theory, well, it's a mathematical theory that can be expressed solely in terms of some operations that are governed by some equation. So if you can describe your theory just with operations and equations, then that's called an algebraic theory. Example is a monoid, a group, a ring, but not a field. Because when you have division or inverses, there is a problem with the inverse of 0, and that's not a total operation, and there are complications and so on. Another one that's not algebraic is a poset. The theory of a partial order is not algebraic, but the theory of a lattice is, because you can describe meets and joins using just equations. And then you have an induced order using meets or joins. So in an algebraic theory, traditionally, we have n-ary operations on some carrier set for type C. So a constant would be a zero-ary operator because it would go from C to the 0, which is 1, to C. So that's an element of C. Addition on the reals would be an example of a binary or two-ary operation. It's better to say binary. And you can think of many other such examples. So that's just the starting point for traditional universal algebra. You look at these operations. Now we're going to generalize them in two directions. So the first direction is that we're going to allow arbitrary variables. So this is actually a general recipe. I think John Baez must have written like this a number of times on the internet. when you see a number, you should ask yourself, does it really have to be a number, right? So if I ask you how to generalize the additive here, many people would say, oh, you can use infinite cardinals. Well, you can, but that kind of misses the point. So we're going to do something else. We're going to allow, so here, instead of a number n, I could use any set with n elements. That would be the same effect. If I have a set with n elements, that the same functions from there to c is the same thing as the nth power. Okay, but then I could say, oh, but I could just have any set. So if I have any set A or type, doesn't matter, object, doesn't matter, presheaf. So if you have any set A, then an ARE operation would be something that goes from C to A to C. So you can recover the all operations by taking here a set with n elements. What are some strange examples or not so strange examples? Definitely integral from 0 to 1 has this type. And you might want to live in a world where all maps are integrable so that you don't worry about whether this exists. That's a minor point in a way. But it takes a function on 0, 1 to r, and it gives you r, a number. So that would be a closed interval to 0, 1 array operation, because you can do this as taking this many numbers as an argument. Another one that comes from logic is the universal quantifier on some set A, because it's going to take a predicate on A, which is a function from A to prop, and it's going to give you a prop. This should be prop here. Yes, maps to prop. So that's an example of generalized additive. You can do strange things with additives if you are in an intuitionistic setting. It's a lot of fun to take a set A, which doesn't quite have one element, but neither does it have 0 elements, and then strange operations arise, and they're used in the domain theory. You can use them in synthetic domain theory. It's fun. So the other dimension in which we want to generalize operations is that we want to equip them with parameters. So what does that mean? Sometimes an operation takes an additional parameter. So if P is some set of parameters, a P parameterized operation would, in addition to doing whatever it's doing, take an additional parameter. So what are some examples for mathematical practice? Scalar multiplication. When you multiply a scalar with a vector, you could view that as a binary multi-sorted operation, because there are two sorts, the scalars and the vectors. But you could also view it as an ordinary single sorted combination, which takes a vector to a vector. So the additive is 1 here, right? It takes a vector to a vector, but it has that additional parameter, which is the scalar by which it's multiplying. And there are different ways to turn this around. You could also say you have, for each real number, one algebraic operation, but it does matter that you have these parameters internalized. So this is also something that I want to have in order to arrive at the idea of algebraic operations, of computational effects as algebraic operations. Another parameterized operation is consing in functional programming, because you take an element and the list, and you attach this element to this list, you get a new list, and you can read this now as an operation that works. The carrier is lists of P's, and the parameter is a P. So that would also be an example of a parameterized operation. Any questions? So now we're just going to put both of these together. So we're going to say, if I have an ARE P parameterized operation on C, that's going to be some map that takes parameters P. It takes a many elements of the carrier, and it produces a result. I just put them both together. So I hope this is okay. I can do this. Okay, but now what I have is already enough to start expressing computational effects. So I'm going to go through one example of how you can now use such operations plus equations to express how a computational effect works.
Great.
Yes.
Could you maybe explain again how do we read the type of the integral? Is it saying that it can take any number of parameters?
So, if you're going to integrate a function from 0 to 1, your argument is going to be a function from 0 to 1, 0, 1, r, right?
I think I don't understand what the 0, 1.
0, 1 is the closed interval of it's all numbers between 0 and 1. All real, it's a closed interval.
Okay.
Yeah. So
like a refined.
I will take this opportunity to do analysis. So well, like this. So this is my function f that I want to integrate, right? So my operation takes an f and it gives me a real number. So it's an operation because it takes something and it gives a result. But let's think about how many things does it take? You could say it takes one function. But instead, you could say it takes very many real numbers. For every element of the closed interval, I have one real number. Is that answering the question?
Yes.
So that's how you can think of it. Okay. Any other question? So maybe it's easier to understand this one. For all takes very many truth values, and then it computes their infimum. That's one way also to say it. You could say, oh, it takes a single predicate. Well, but a predicate is just very many truth values, one for each element of the domain. Okay, so let's do an example. State. Okay, we want to describe state using operations and equations. So let us fix a set of states S. And then we're going to have two operations, which are to get the current state and to set the current state. Let's call them get and put, because those are nice names, because each one is just 3 letters. So get receives the current state and put sets the current state. Well, let's write down their types. Okay, so here it's important to understand what C is going to be. So far, I said C is some carrier. So in a way, we don't care what C is. And in fact, these operations in practice will be polymorphic in C. So C is whatever we're computing. So something we're trying to compute. So what do we do? Okay, so why is get like this? What do when you say I read the state? What happens? Well, say I read the state, I get an element of S, right? I get some X element of S. I get the current state. Maybe just so it's clear, this is the set of all states. Okay, sometimes I think this is a confusion. This is the set of all possible states. So this is the memory in my PC. It's a lot. It's all possible configurations of my memory. It's 2 to the number of bits. It's not the number of bits. So, okay, so when I read state, I'm going to get an answer, and then I will do something depending on that answer. So what I will do is a function of the answer. So I will say, I want to get the state. The state will come as input to whatever I'm doing next, the continuation. And then, depending on the states, I will produce a result in C. So if you wrote this, for instance, let's have an example. Suppose my state is just natural numbers. And I want to do the following. I will read the current state. So my state is a single cell of memory that contains one natural number. I want to read the state, and then if it's an even number, I want to calculate true, and if it's an odd number, well, let's say I want to, if it's an even number, I want to output 0, and if it is an odd number, I want to output 1. Okay, something like that. Okay. So the way I would write it using this operation get is I would like do it like this. Get, and now I need to apply get to what will happen afterwards. So I will get my number, and now I explain what to do. I say, well, if it's an even number, then output 0, otherwise output 1, something like this. So the way you think of this is to say, okay, an operation is going to happen. The result of the operation is going to be received by this bit here, which actually does all the work afterwards, the continuation, and then it does whatever it does with the state that it receives. Is that clear? Yes. Yes.
How would, like, in terms of like type checking,
Yes.
how that's just a lambda function.
Yes.
How would that type check to be like CS to C? How is that different to just anything else?
Well, I mean, so first of all, maybe this will make it clear, but S to C is exact. This is the same thing as this function space. Does that help?
Right. Yes. Okay.
That helps? Yeah. Okay. That's just a different notation for the same thing. Okay. Put. Does put make sense? Well, suppose I want to do the following. I want to set the state to 42, and then after that, I want to compute 7. Well, then I would say something like put 42, set the state to 42, and then do something else after that. So it's actually a 1. If I'm very exact, I should have a 1 up here so that I know that it's a unary operation. If I don't, I just do something, whatever I do, like, do something. If I want to be a little more exact, and I did put 1 in there, I would write here lambda, I will receive the unit, and then I will do whatever I want to do. And to be even more exact, I would write return here, to indicate that I'm not triggering any new operations. So now you say, perform this operation put with this parameter 42, so set the state to 42. As a result, you get the unit because it's a unary operation. When you set the state, the result that you get back is unit. And then you continue calculating. Question? Yes?
So what is actually C in this case?
Yes, so C is the type of the end result I'm going to compute.
Okay.
And in fact, when these things are implemented in in programming languages, get will be polymorphic in C, because I can read state and then calculate whatever type I want. I'm not restricted to what the result will be after I've read the state. So C is the result of your final. It's a type of the final result that you get.
What is it in this case? Like in that?
In this case, C would be, so in this case, this is a function that goes from unit to not. So this would be C, would be natural numbers, because once we calculate this, we will get a number 10. So the end result has type not. And up here, it was also not. My imagination is really poor. I'll do better afterwards. Okay. Would anybody venture to suggest any equations that these things follow? Maybe just at an informal level. So let me ask you the question this way. What's going to happen if I read the state and then I immediately read the state again? Can I tell what's going to happen? What will happen? I'll get the same result twice. Yes? What if I set the state and then I immediately read it? Do I know what I'll get? Those are equations. Okay? So there will be 4 equations explaining all 4 possible combinations of get and put. Let's have them. So let's read them to see whether they really describe how state behaves. Okay? If I read and I get an X, then I read again and I get a Y. That's the same as reading once, you get some Z, and then you do whatever you wanted to do, but you use z both for x and y, because you know that it's going to be the same. X and y will be equal. You are just read states twice in a row. Yeah. Okay. Okay, the next one. If I read state x, then I immediately set it back to x. Did I actually have to do that? No, I already knew it was x. There's no point in setting it. So I can skip the putting. I don't have to write it back. Okay, the next one. If I set the state to x and then I read it and I get a y, what do I know? Well, I know that y would be x because I just did that. So that's the same as just setting the state, setting state to x. Then I don't have to read it. I can use x instead of y. And the last one is, if I set the state to x and then I set the state to y, then I know that only the second one worked. So only the second one matters. So I could just set it to y immediately. I don't have to set it to x. So these are equations describing state. Are there other equations that we might be missing? Well, that's a good question. But people have proved no, there are no other equations that we're missing. So they have the following property. If you add an equation to this system that doesn't already follow from these four, you will get a trivial theory. So in a way, it's separated. It's what is this called? Hilbert post-complete. So there are no more equations missing unless you want to describe trivial theory. And they are clearly explaining how state works. We agree that this is how state works. So this is an example of an algebraic effect. We have described a computational effect in terms of algebra. This theory goes back to the work of Plotkin, Gordon Plotkin and John Bauer in the early 2000s. But I think the idea is present earlier than that. I was once told that John was sort of jumping up and down when Eugenio Moggi explained monads as computational effects, and he was going, no, you should use algebraic theories. But that was in 1980 something. So anyhow, this theory has sort of taken off as a refinement of monads, effects and monads, because every algebraic theory induces a monad. And there is a close connection, and of course there will be monads present everywhere in what I do because they are just there. But the focus here is on how the monad is presented. It's presented in terms of operations and equations. How wide is the scope? It's wide. So you can do all kinds of, you can describe all kinds of effects this way. So for instance, I/O. Well, I/O is going to be a bit similar to get and put, right? Because it has a read and a write, input, output. But these equations, there will be different equations. I can tell you what equations there will be for I/O. So instead of get, you have read. Instead of put, you have write, but they have the same type. And there you don't have any equations, and you get I/O. You delete the equations, state becomes I/O. Then exceptions are a special case. Because, so let's think in terms of monads. What's exceptions? So you want to have raise or throw. Let's just say we have a raise that doesn't carry any information, just raise, okay? So what does that mean? Well, the type of raise, so if you want to raise does the following. This is a nice one. So every operation looks like this. You have an operation, and then what are you gonna? Then you have what the thing you're going to do afterwards. So what you will do after the operation? I will read state. Then depending on what I get, I will do something. I will put 42 into the state, and then I will do something. So for raise, you also have to explain what you will do afterwards. But you will not do anything afterwards. When you throw an exception, you're gone. You never come back, right? You throw an exception, you're done. You cannot come back. So how do we say that we're going to do after, that we will do something afterwards, but we're not going to, we're never returning, yet formally we have to write something. You could be option. You could, well, but I have to explain what I will do with the result of, like, I have to explain what my continuation is, except there is no continuation because I do not intend to continue. The point is that this is going to be empty type. Okay. So, raise, we'll get to your option. What is raise as an operation? It's a zero-ary operation. Because when you raise an operation, when you raise, you are going to get a result from the empty set, which is to say you are not going to get a result. You are not going to, the operation is not giving you back the control so that you can do something with the result. And the way you say that is, yes, there is a result, but it's from the empty set. That's the same thing as saying it's not there. So raise is actually a constant. And because of that, if you now calculate the monad, you're going to get option. Yes. Non-determinism, probabilistic computation, these can all be expressed. These are all well-known monads also in terms of monads, computational effects as monads, but they are of the kind that is algebraic. And then you can do various variations on memory, and we're going to use a variation on memory today. And then you can do weird things like cooperative multi-threading and delimited continuations. Why? Well, because essentially when you have an operation, the thing that is here is your delimited continuation. And so you can grab it and say, oh, this is my thread. And then there are examples like that. There is one famous non-example. Undelimited continuations form a monad, but they're not of the algebraic kind for mathematical reasons. And I'm not going to get into it. Yes?
What about higher order operations like catch?
Yes. So that is a very good question, because that's the next slide. Right? What is catch? So the story, by the way, the story goes like this. John Bauer and Gordon Plotkin invented algebraic operations, and all kinds of things were operations, but catch wasn't. Catch doesn't work. Like you try to write it down as an operation satisfying equations and you fail. And so they were wondering what to do. And then Gordon had a student, Mattia Pretner, who did in his PhD, he gave an answer. Catch is a homomorphism. So that's the next slide, I think. Okay? So there's some math. And the math says that a handler is a homomorphism from a free algebra. And I do not expect you to understand what this is now, and I'm not going to do this mathy stuff now. This is the kind of thing, if you're interested, I'm happy to explain it on the board during the coffee break or sometime later. Find me, I can explain how handlers are homomorphisms from free algebras. I will now explain, instead I will explain it the programmer's way. I will explain how handlers appear as a programming concept, because that's what we're going to use them for. So I think it's more important to understand that aspect of handlers, but it's really the connection is tight. They are also homomorphisms. Okay, so there was a question about catch. Catch is an exception handler, right? So let's compare them. Algebraic handlers generalize exception handlers. So an exception handler will intercept an exception and then it'll do something. An algebraic handler will intercept not an exception, but any operation. It can intercept any operation. It can do something. It can also, among other things, resume the execution from the place where the operation was performed. So it can go back to the place where the operation happened, and it can pass information there. So that something happens depending on the information you're passing. Where is the information? The information is the arity of the operation. So an operation will come to the handler. it's going to have some parameter P that the handler, like the location of memory that we want to read, the string that we want to print out, stuff like that is here. This is the information that the operation is sending out. Just like an exception can also send information out. It can carry information. That's the parameter. And then here, you're going to have some continuation. And this continuation is a function. It's something that goes from A to C. So this means the handler will be able to restart the continuation by passing some information to it of type A. For instance, if an operation wants to read from a file, this could be the file handle, and A would be string. The operation wants to read a string from a file. So the arity is what the operation results in. It looks like it results in something. So one way to understand algebraic operations is to say they are like resumable exceptions. They're exceptions that you can sort of change your mind and go back and continue. And the handlers are then the appropriate notion of handler for resumable exceptions. In fact, there is a version of WebAssembly where they introduce handlers and operations into WebAssembly because that covers a lot of ground. You saw the previous slide that you can do all kinds of things with them. And for marketing purposes, they did not want to call them handlers because that would scare the true programmers sitting on the committee. So they call them resumable exceptions, which sounds a lot sexier and more acceptable. Okay, as a programming tool, how do we use handlers? Okay, so one way to use handlers is you modify existing effects. Somebody's printing, you wrap them in a handler that intercepts print and does something else instead. Maybe it redirects the output. Maybe it secretly sends the output to a friendly nation, stuff like that. Or maybe you want to log all memory accesses. So you would intercept reading from memory, and every time you read from memory, you would reissue the read so that some outer handler will get the memory, but you would also, in some logs, say person X accessed this on such and such date. So you can do that kind of thing. This is modifying effects. But also, this is what Haskell thrives on with monads. In Haskell, you can use all monads to implement effects, or to say to simulate them in a pure environment. And now you can do the same thing using handlers and operations. You declare some operations, and then you grab them in handlers that explain what to do about these operations. So it's quite similar. It's a different style, but the end effect is the same. You have a pure environment with algebraic effects and handlers in which you then can write programs in imperative style to achieve much the same thing. Any questions? I think we want to see an example. So I'm going to show you an example. I could show you trivial examples. I didn't want to show you trivial examples. I wanted to show you relevant examples. So let's implement in OCaml 5, which supports handlers natively. Let's implement write once state. So we want to have get and put, but we want to do it in such a way that if I try, I can write to the state once, but if I do it again, it's an error. I can only update once. This is relevant for us because a meta variable can only be updated once. It cannot be updated more than once. Yes?
Is it a compile time error or a runtime error?
We are going to make it an exception because this is all in runtime. It's me, the programmer, implementing a new kind of effect. It's not me, the compiler designer, implementing a new kind of effect. The compiler designer already provided all the effects there can be, which is essentially everything the operating system has to offer and the way the computer works. It's the real effects of the real world, hardware, files, stuff like that. While when I'm inside my language and I'm playing with handlers, I am I'm simulating effects as a programmer. It's the same as in Haskell. In Haskell, when you implement state, you get the program is still pure, right? It just looks like it's doing state, which it is. Okay, so let's go through these lines here. I know it looks a bit scary, but we'll go together. So what do? Okay, so first, you declare some new operations. Just like you can declare new exceptions, you can declare new operations. So I say there's going to be an operation get. It takes a unit and it returns an integer. So for simplicity, my state is going to store an int. Put takes an int and then it returns unit. Yeah. These are just our put and get from before. But this is how you write it in OCaml 5. Okay. Now it's convenient if you actually want to perform these operations, you have to say perform blah blah blah. And I don't want to keep writing perform. So usually people define shorthand functions. So these are just auxiliary shorthand functions that just trigger the operations. This is just readability, but I think almost everybody does this. It's annoying to write perform everywhere throughout your source code. Okay, then we need to model memory. So we're going to model memory because OCaml already has references. We're going to model memory using a reference. Okay, we're not afraid of references. We're OCaml programmers. We're not Haskell programmers. But we need to remember whether the state is its initial state or whether it has already been modified. So I have an auxiliary mode type, which is going to be used to know, have I already updated my memory? So in the beginning, the mode will be initial. As soon as I update, I switch to modified. And then if I try to modify a modified one, I complain. Okay, so now we have to write the handler. So a handler looks like this: try, with, and then here you can catch exceptions, and you can also catch effects. Exceptions are just special effects. Exceptions are nullary effects. So the way this is usually organized, or that I would recommend, is like this. You write a little wrapper function that is going to wrap a handler around whatever you want to do. So this is a tongue. So some computation that you want to perform as a function of unit so that I can trigger it at the right moment because we are in call by value. So I have to do this. So I will trigger my computation and wrap around it my handler. So let's see what the handler does. It says, if the effect get happens and K is your continuation, K is this thing, the thing you should do if you want to resume. Okay? Well, in OCaml, they don't say resume, they say continue. Same thing. Then you can continue with K, but return the second component of our reference. Okay, so what is our reference? R, it's here. So at the beginning, we have the initial state S. So it's a reference, it's a pair. The first component tells me what the mode is, and the second component tells me what the state is. So I dereference, and I take the second component, which is this. So that's what get will do. It'll return current state. Okay, how does put work? Well, if the user wants to, this computation wants to put the state S, then I have to look at my R, and there are two possibilities. If I'm still in the initial state, and I don't care what the initial state is, then I will update the state here, but set it to modified, because now it's been modified, and then I will continue with the unit. If the state has already been modified, I will now raise the exception invalid, right? Which is going to propagate outwards. And somebody has to do something about it. Questions?
In OCaml, the C tongue doesn't indicate what kind of effects it can.
No. Types. Okay, yeah, this is why I said that Haskell programmers will feel dizzy. In OCaml, the types do not carry information about effects. So you don't know what this thing is doing. It could also be triggering any kinds of other operations, which then would be caught possibly by some outer handler somewhere else. and you don't know that. And it's up for discussion whether that's a good or bad idea. Opinions are divided. I think most people think it's a good idea to have at least some information about what effects might happen, because when you program, you care about this. So people do work on the so-called effect systems, which equip types with information about what effects might happen. But these effect systems tend to get hairy quickly, because you get into constraints saying, oh, I know at least these many effects happen, and then if this function has some effects E, then my output will be E union something that I'm doing. But then a handler comes, and then you reduce the effect. So it's a small sub branch of PL.
Is it really hairy, or is it just row polymorphism?
Ah, yes. So you would think it's just row polymorphism, but then it's you really want subtyping.
Okay. Yeah.
So it's row polymorphism with subtyping, and then the question is, how fancy do you want to get? There is a practical question: is that, well, maybe the compiler can handle very complicated constraints, but then when something goes wrong and you have to explain to the user what goes wrong, you don't want to show the user 3 pages of constraints and say these constraints are not satisfiable. The user will not be happy. Any questions? So now we're going to use this technique or similar techniques to implement things. Oh, let's see how this would be used. Okay, let's have just 2 very simple examples. So if I want to have this write once state, I would grab my computation as a thunk with this function. I initialize to 42, and then I write OCaml code as usual. No monads, no more stars, just direct code. And so I should say that the execution mechanism for operations in OCaml is similar to how exceptions work. And they made sure that it's quite efficient. So get the state, so we'll get 42 with the state, so that's 46. And then I will return 42 plus whatever the state is, 42 plus 46, hopefully is 88. Okay. So if I try to put twice, then I'm going to have a problem. So question, will I have a problem? So now I have to calculate whether 42 times 42 is more than 666. And it doesn't take long to figure out the answer. It's, it's way more. So this computation will put once, the memory will go to the modified mode, and when it comes here, it'll get an exception. So this one will raise an exception. Okay. So now let's try to do variables in our little proof checker. So the first thing that's going to happen is that we will remove the context monad. Remember, we implemented in earlier versions, in the earlier 2 versions, we said, well, you could write your code with your bare hands, and then you have this boilerplate that keeps passing the context everywhere, and it's kind of annoying, and the code looks ugly. So let's wrap it in a nice reader monad. And then yesterday it was a combination of a reader monad and a state monad, but you wrap it in a monad, and then you use the do notation, or in OCaml it's let star notation. The result is that everything is going to be wrapped with your little monad. So you'll really be calculating lots of little closures, or you hope that the thing will compile to something better than that. Now, there is no more monad like that. We don't have to have any explicit monad. We'll write direct OCaml mode. Where did the monad go? It's still around because we still have effects. The monad is now the huge background monad of OCaml. OCaml itself is running in some monad style thing, which is on the fly extended by new operations. So that's what's going on. And then the handler it's just not visible in the typing system anymore. It's not visible in the code, but it's kind of a background monad that's happening. Okay. Let's do operations first. So some of this looks like a triviality. It is a triviality, But then you will see when I combine with meta variables that it's not a triviality. But so at first it's going to just look like I'm playing around with giant. Okay, so first we think about what will be our operations. Okay, so the operations will be that I want to look up the information about a variable. So I give the variable and I want to see its optional definition and a type. That's one operation that I want to have. Then I want to look up an identifier, that is to say a concrete name, and I want to see what it's associated with, which variable. And I will also have something that allows me to define global entries. So I can have at the top level, I can have a definition. This is at the top level, I have a definition, which I can run an operation. I say this string is a new string that I'm introducing at the top level. Please create a variable and then associate it with this operation and possibly with this definition and this type. And it should just happen. So unit. I don't see what it did, so I get a unit. I don't get the context back or anything like that. Somebody's taking care of it. It's somebody else's problem. Those will be the operations that I want to introduce, and I will have little wrapper functions for them so that it's more convenient and so on. Okay, what kind of handlers will I have? So I'm going to have a one handler for global variables. And there's just one such instance of this handler, and it's at the very top level, because when I'm processing top level commands, they all share the same state of global variables. So somewhere in the main program, on the outer level of everything, there is going to be an invocation of some wrapper function that handles the context. So the global context. And now, here's a trick. What do I do when I introduce a local variable? Well, then I'm going to have one handler per local variable. And these handlers will be nested the way that local variables get nested. If you have a let, and then you have another let, and you have another let, that's going to be three handlers stacked on top of each other. Each one will be taking care of just one variable, one local variable. It's a little silly, but with the meta variables, there will be an additional functionality. Okay? So let's have a quick look at how. So I'm not going to show you all the code on the slides. We can look at it later. I will just sort of give you an overview. Okay, so how are we going to handle the global context? So if I want to handle the global context, and this is my continuation, the thing I want to run. So I start with the context that's a reference to the initial empty context. I run my computation, and now I need to handle all three operations. But this is not going to be anything special. Somebody wants to look up a variable. Well, I have this is the same kind of context I used to have. It has a map for identifiers. It has a map for variables. So I just look it up and return it and so on. So I can look up a variable, look up an identifier. It's just lookups. And then I pass the information I found to the continuation. And the top extend, well, the top extend is going to take the information and it'll actually extend my context and run the state. So this would be just a standard state handler. It's not really necessary, in fact, because OCaml already has state. I could just literally use this reference directly in OCaml to do the same thing. But I'm wrapping it like this with operations because that gives me the ability to intercept them. I can intercept some of them. For instance, this is only going to take care of the global variables. What if somebody wants to read a local variable? Well, then there will be another handler that intercepts that local variable. So that's the next one. So the local variables, first let us think, where do local variables appear? Well, they appear whenever my context gets extended in my typing rules. So which typing rules extend the context? Let, and lambda. They introduce new variables in the context. So each one of these is going to introduce a new variable. How will that work? Well, like this. We're going to have another wrapper. And the idea is that I want to run C in an extended context. So C is supposed to run in whatever variables already exist, plus one additional variable whose concrete name is X. It's the abstract variable is V, and it has an optional definition, and its type is supposed to be T. So now I want to write a handler that's going to intercept my operations for variables in such a way that if somebody's asking about X and V, I answer. And if they are asking about something else, I say, I don't know. I pass it through. So you can do it with the guards here on the handler. So you say, okay, run C. And if C is trying to look up an identifier Y, provided X equals to Y, so they actually are trying to look up the variable that I am in charge of, then I say, oh yeah, I can tell you what variable it is. It's the variable V. So if the lookup, if this Y is different from X, this is not going to trigger. It's going to propagate outwards, and somebody else will take care of it. And hopefully, if nobody else takes care of it, it will be the top level handler for global effects. And if that one doesn't work, well, that one will actually return none if it doesn't know. Okay. If they want, if they're looking up some variable W, so this is an abstract, this is a string, this is an abstract variable of bindlib. Well, if they're asking about our variable V, the one that we're taking care of with this handler, then I answer. Here's the definition, here's the type of this variable. Again, if it's not V, then this does not trigger. And now what I do is whenever I want to compute in an extended context, I just wrap my computation with this helper function, and it's just going to work. Questions? Okay. I think I said all these things already. Yes, so the handlers will be nested the same way the local variables get nested. This has certain consequences. Access to the variables is going to be linear time, like in De Bruijn indices. Because if somebody wants to have access to some variable, and there are 7 handlers stacked up, each one of them is going to say, is it me, is it me, is it me, is it me? So that's linear time. So I am not suggesting you should rewrite ROP this way. It's, yes?
Can you propagate exceptions with handlers when you nest them? Would you say, okay, I'm type checking the if statement.
Yes.
And it sort of says if A equals B, then 5 else false.
Yes.
And
so I discovered that there's a typing error.
Yes, but sort of the usual thing is that then you go into one of the branches, let's say the branch with 5, and you say, oh, there's and then you infer, okay, both branches should be integer. You go to the latter branch and say, oh, here I found a bool where I expected an integer. Right? But maybe the error message you really want to give the programmer is the branches of this if statement are inconsistent.
Sorry, I'm not. It's not clear to me. Are we talking about how the type checker works or how the evaluator works?
No, how the exception propagates.
How the exceptions propagate.
Yeah, so you throw an exception from, let's say, one of the branches of an if statement.
Yes.
But can you then sort of propagate the exception and say, oh, actually, I wanted to throw a different exception, the one that says, oh, this whole thing is inconsistent. Well,
maybe instead of having the if statement, you would have a sort of weird if statement that also catches exceptions from its branches or something. I mean, I don't think the mechanism for exceptions is the same as always. There's nothing new about it. So if you can do it with exception handlers, you can do it.
Okay.
There's no additional magic about exceptions. The only additional magic is that I can catch not just exceptions, but also operations, and I can resume them. That's the magic.
Right, okay.
So whatever you can do this way, I don't know if I don't think I understand your question, so I don't know if I'm answering.
Okay, I will re-ask the question.
Okay. So that's variables, it works. Now, what about meta variables? Well, meta variables are going to have some additional operations. So for meta variables, we are going to have operations that look up the information about a meta variable. I give you the abstract bindlib variable, and you give me a possible definition and a type. Then it should also be possible to create a new fresh variable, and this underscore is here because of bindlibs, because bindlib wants things boxed, and it turns out that when you're implementing this, you want the boxed version, so ignore the underscores, okay? Just pretend they're not there. So how do you create a fresh meta? You say you give it a name. So somebody, like, just so that you can print it out later, you give it a name, and then you say what its type is. And then what you should get back, oh, it's interesting. What should you get back? Because once you have a meta, now we have to remember what we did with metas. So yesterday, there was this example. It said, suppose I have type A, I have A, then I had lambda x question mark h x applied to A. That was the example. So I have a type, an element of the type, and now I apply the identity function with an unknown domain type question mark h. That's my domain, that's my meta, applied to A. So what we want at this point, remember what is it that we want? We want to say something like this. We want to say here, create a new fresh meta, h, and its type should be pi A in type, A in A type. Because of what? Because this is a type, this is a checking position for type, so it needs to be a type, but we're going to close under local variables. Yes? So we get a product. This is the type that we want. So we want to create a meta of this type, but then once we do, what do we insert back in? So we're going to insert back in h applied to little a, big A, little a, and let's maybe put primes here so that we don't confuse things. So this a and this little a, remember, we applied like that. So we said we're going to have a function. So the meta will really be a function applied to these things. Why was this? Because we insisted that metas need to be typable at the global context, not some local context. So we want the close, so we do this stuff here. So when you create a meta, you specify its type, but then what you expect is that you will get back this application. Because you can't calculate this application by yourself, because you don't know what local variables there are. The local variables are just some handlers up there somewhere. So it's those handlers that needs to help with the computation of this application. But the point right now is that when you create a meta, you say what its type is, but then what you get back is a term that you will insert for the whole. Because the term that you will insert for the whole is not a pure meta. It's a pure meta applied to all the local variables. That's the fresh meta. And then there also has to be a way for setting the meta, where you say, oh, I want to set the meta such and such variable. I want to set it to such and such term. And I want to find out whether I succeeded, because if I did not succeed for some reason, somebody blocked me. Maybe it's one of the local variables said, no, you can't do that because it appears. So if it's false, then I proceed. I have to know whether my unification succeeded or not. Questions? Okay. So there will be now a handler for meta variables. And let's think about where this will appear. So if I put this handler at the very top level, then all the top level definitions will share metas. So you could have a meta variable appear in the first definition, and then it could be resolved only in the 7th definition when unification figures out what it's supposed to be. Usually, that's not how proof assistance work. Usually, a proof assistant says that if you have a top-level definition, then all meta variables need to be resolved. You have to figure out what the holes are by the end of that definition. So that tells me where to put the handler. I need to put a handler around each top-level command. Each top-level command gets handled by one of these. What does this handler do? Well, it needs to take care of these operations. What will it look like? Well, lookup, that's like reading state. Set is like monotone set state, right? We just had that. And the fresh needs to come up with new metas. So it's going to be a lot like just some state. Yep. We still don't know exactly how to do this business of wrapping the type of the meta with the local variables, because my program, my type checker, does not have access to the context. The local context does not exist. It's in the handlers, it's in the control structure. So the control structure itself needs to help with the construction of this type. And we're going to look at how this is done. There was a question? Yes?
Yeah, so defining a function is also a top-level command, right?
Yes?
But if the function has implicit parameters, then we can't resolve those after the definition.
Oh, but if you are defining a function with implicit parameters, which by the way, we don't have. We don't have that. But if you were defining a function with implicit arguments, that just means that you would define an ordinary function, but in the pi type, you would have a little flag that says, this argument is implicit. And all you have to do is tag with implicit, because I'm not calling the function yet, I'm just defining it. Yeah. Does that answer? You don't have to do anything about implicit arguments when you're defining the function with implicit arguments. Only when you use it, you have to start filling in the holes. And then things will happen.
So you don't create meta variables at definition
Time.
point, but at usage.
At the usage time. That's where, because each usage should get its own meta variable.
Yeah. Right. Okay.
Yeah.
I'm sanity checking my own implementation, and
Yes.
it seems correct.
You're
So
not
that's good.
frantically typing git abort blah blah, so it's okay. Yeah. Okay. Yes. So we should look at this, and I will drag you through a little bit of code now. Okay. So what's going to happen is we're going to look at these handlers. So with metas, handle here. Here is the handler for metas. How does it work? Okay. So you want to handle meta variables of some computation C. Oh, before that, let me show you how it gets used. It gets used in the top level. No, I keep thinking it's handle metas. So I have a top level definition. I do whatever I want to do, but it is wrapped with all my handler. And each one is like that. See? Handle metas, handle metas. So each one gets its own handler. They don't share the meta variables. So what do? Well, first we create the state. This is the same. We have a reference that stores the relevant mapping for the meta variables. Then we run. What will we do? We're going to run our computation. After the computation returns some result R, we're going to check that all the meta variables have been resolved. If they have not been resolved, we're going to raise an exception, and then we will return R. The more interesting part is, what do we do with effects? Well, but these are not super complicated. So let's see. Lookup, you literally just look up the information in your map. Set is more complicated because you have to do this business of set once. So if somebody is trying to set the state again, I don't even show an exception to the user. I say assert false, the type checker will explode because it's the implementer's error to try to set a meta variable twice. So I want this to be embarrassing for me if it happens. Okay, so otherwise I'm just setting the state, so on, and then freshness will create a fresh variable, add it to the state, and it will. Oh, now look at this. When I create a variable h, then I return just the meta variable. I literally return the meta variable back. But I said earlier that I should be returning the meta variable applied to all the local variables. But I'm not doing that. Well, I can't because I don't know what the local variables are. So I return just the meta. What I do next is I have my local variable handlers, and they are barriers. They are control structures that can see anything that goes through them. So they can see that a meta variable operation is going through. So they will intercept it and fix things. So let's have a look where else this fresh meta is used, is handled. So this is, here it's declared. Here in the handler for the local variables, I am also going to fiddle with the meta variables. How? Let's see, what does it do? So if somebody is asking for a fresh meta variable named x and its type is u, and I'm handling a local variable x, or a local variable v of type t, then what I will do is the following. So here, I'm going to, they want a variable, meta variable of type u. I'm going to change u so that it's a product of t and u. So I'm adding the product in. So each S fresh meta travels through all the handlers for the local variables. Each local variable handler adds its own pi here. So I started with this one at the call site, and then it keeps increasing the pi's. Every time it goes to a handler for a local variable, the pi gets a little longer. Because then it's, now this one is going to be performed on the outer level, right? And so it propagated. But we're not done yet. When the result comes back, the original meta variable handler, it said, oh, it's just the meta variable. But I know as a local handler that I should be applying here. So if I'm the local handler for A, I will get this, I will intercept, I will get this result, I will add myself to the application. So I say, okay, whatever the fresh meta returns, some term E, I'm going to apply my variable, I'm going to apply E to my variable. And this is how they get built up. And then there's a similar trick for set meta that I'm not going to discuss, but there's also something about set meta there. Well, you can actually see a complication because it's also taking care of variables that have local definitions. But let's not get into that. I just wanted to show you this interaction. Is this dangerous programming? Yeah, I think this is fairly dangerous programming. Why is it dangerous? Because the control structure needs to precisely fit, and it's written in different parts of the code. So that's maybe not so good, but I think it's way cool. I mean, it's hacking, right? So it's fun. Handlers in general are known to suffer from the fact that they combine very easily, but unlike monads, but they combine in really surprising ways. So you have to be very careful how you mess them and how you combine them. So you have to pay attention. Okay, so I think I'm going to conclude. So let's just have a quick recap of what we did. So lecture 1 was theory. Then first we had a type checker where we were looking at things from the monadic point of programming. So even though we were in an effectful language on Camel, it still paid off to have an explicit monad, the reader monad, and write the code in monadic style, because if for no other reason, it reduced some of the clutter. Then we added holes, so our monad got more complicated. And if you look at the second version and you look at how the meta variables are done, it's kind of hairy. It's the hairy kind of code that you don't really want to write. You have to be very careful because you need to produce these pies, these products. There's some crazy loop that does the product and the application. And one of them is fold left, the other one is fold right, but you want to do them in a single fold, so then buggy, okay? Today we saw a possibility, just to give you ideas about what you can do using programming language techniques. In particular, algebraic operations and handlers can be used to do all kinds of magic. You can, of course, now go and do the same thing in Haskell using monads if you want to, and it'll perfectly work. It will work just as well because every algebraic theory does induce a monad. Monads are more general. So here's some further reading. If you want to know more about the theory behind algebraic effects and handlers, the math that just hit, there are lecture notes from the OPSO summer school called What is Algebraic about Algebraic Effects and Handlers. This is an archive. Lecture notes explained very slowly. They also explain this general theory of algebraic theory starting slow. Mattia Brittner has a tutorial on algebraic effects and handlers that was at LFPSI at some point. And then the only similar experiments in using effects for compilation techniques or type checking and stuff like that. I know two of them. Bob Acting has a talk. There are slides and video and everything on an algebraic approach to type checking and elaboration. So that's well worth seeing what he does there. And Connor McBride has in his GitHub repository an interesting version of Hindley-Milner that uses effects and handlers. It also doesn't have a context. Everything's in the handler. And being Connor McBride, of course, this is done in a conceptually beautiful way. So first we have a Kripke model, then we have the handler on the Kripke model that makes the time pass, and as the time passes, things get unified. You should have a look. It's a typical piece of Connor's code. And that's it. Thank you. We can declare a coffee break, right? Okay, we declare a coffee break. So, yes. Do I think this end button? No, we don't. Just the ones we have